Sir, can you start the recording?
Yeah, I have started. It's not started yet. Yeah, it has been started.
Yes, sir. Yes.
It has been started. Okay. So, welcome you all for the chapter that is that is its name of the chapter is Canonical Form, or rather we can say Canonical Forms of second order partial differential equations. Okay. So, uh, the most general case of second order linear partial differential equation in two independent variable is given I can write R plus BS plus CT plus DP plus EQ plus FZ is equal to G. Okay, so say for example, this is 1, and we can write this as now Z is the dependent variable and X and Y, these two are independent variables. These are very standard things I'm writing. And what are A, B, C, D, E, F, and G? These are all functions of X and Y up to your G. These are all functions of X and Y, and possessing partial derivatives and these are of course continuous function, continuous and possessing partial derivatives in some domain D on the XY plane. Clear? Okay. So earlier whatever we learned, that is particularly constant coefficient, but here these are not necessarily always constant. These are functions of X and Y and continuous functions, and still possessing partial derivatives, second order partial derivatives, so that we can use certain properties. Okay. But at the same time, since we are looking for the second order partial differential equation linear, then we have to put another restrictions like A, B, and C. These functions cannot be zero at the same time. So we can assume another restrictions like A, B, C not zero simultaneously. What happens? What will happen if A, B, C will vanishes? The given differential equation will become, or the given differential equation reduces to 1 degree less. That means first, sorry, 1 degree, uh, 1 order less. That means first order differential equation, PDE. Okay, so that we don't want initially, because we are having a second order linear partial differential equation, which is in general form. We like to solve that differential equation by using some technique. What kind of technique? There are different techniques we are interested, or in our course we need to reduce this system to its canonical form or standard form, from where it is very easy to find the solution. Okay, so there are other methods also, but those methods are not there in the syllabus. Okay, so I can write this equation in this way. The same equation number 1 in this way: AR plus BS plus CT is equal to functions of X, Y, Z, P, Q. So I can write this is as number 2. Okay, because the classification of second order partial differential equation depends on the form of the leading part of the equation consisting of the second order terms. Okay, so should I tell what is R? ZXX, what is S? ZXY, what is T? ZYY. Okay, and ABC, this is basically mostly it depends ABC, these three coefficients. So I can make it in the right hand side. So right hand side is a functions of X, Y, Z, and ZX and ZY. This is your ZX. These are the standard notation, as we already learned about these notations. Actually, there are three types of PDE, which are known as hyperbolic, parabolic, and elliptic. Okay, so there are basically three types of partial differential equations. One is hyperbolic, another parabolic, and the last one is elliptic. Okay, so but how to know that which kind of differential equation is a particular differential equation is this? Okay, so for that we have to depend on ABC, and we have to know certain equations and certain things. The first one is like for the hyperbolic at a point at some point, maybe x comma y in D, if b square minus 4 AC. This is the discriminant. Sometimes it is denoted as delta. This is greater than 0. Number 2, it comes to the parabolic type at some point x comma y in D, if b square minus 4 AC So these are the functions of x and y, then definitely if you put some xy, then if it is going to be equal to 0, so there you can say that and this differential equation is of parabolic form. Number 3, elliptic. At some point, provided you understand possibly this is b square minus 4ac is less than 0. Okay. Okay. If we look at the physical point of view, then each of the category related to specific problem, like the Laplace's equation for the first type, this is like your zxx plus zyy is equal to 0. So there is only there is no mixed type differential equation, only xx and yy. There is no first order differential equation also. So this is Laplace's equation. Another equation is known as the wave equation, and its form is zdt is minus zxx, or sometimes it is known as zdt is equal to c square zxx. Some constant c is there. Another is heat equation. So this is of the form zt, first differentiation, and in the right hand side it is second xx. So zt is equal to zxx. Okay, so these are the three equations, fundamental equation. If we see from the physical point of view, physical phenomena, and then and these three basically are of the above three forms. First one is this, second one is this, and third one is this. Okay, so we'll be coming to that. Okay. So whatever we can say, hyperbolic equation model the transport of some physical quantities such as fluids or waves, and parabolic problem describes evolutionary phenomena that lead to a steady state described by an elliptic equation, and elliptic equations are associated to a special state of a system in principle corresponding to the minimum of the energy. So mathematically, these classification of second order partial differential equation based upon the possibility of reducing the given equation 1 by the coordinate transformation. Basically, we have to use some transformation. Initially, independent variables are x and y. We like to apply certain transformation to make it another set of independent, maybe u comma v. So this coordinate transformation we have to use. Okay. And then I like to discuss certain methods and techniques for solving PD. Number one is this change of coordinates. By changing a PD can be changed to an OD. PD can be changed to an OD or to an easier PD. PD is there, but we can change it to some PD which is easier than the previous one or the original one. So that is again, this will help to solve the PD. Okay, by change of coordinates. Actually, this is interested. We are interested to this. This thing is, we will be interested. This is in our topic. Topic included. Topic of interest. Okay. Number 2 is separation of variables. So this is a very standard techniques, but unfortunately this time particularly we are not able to cover this part in your syllabus. So separation of variables. A PD in n independent variables is reduced to n ordinary differential equation. So in this method, what actually it can be done, a PDE in n, though we are, this is for general PD, okay, n independent variables is reduced to n ODE, okay. So then it becomes easier to solve the ODEs. Number 3, integral transform. So these are not the scope of our syllabus. APD in n independent variables is reduced to 1 in n minus 1 independent variables. That means n independent variable PD, it is reduced to n minus another PD, which is of n minus 1 independent variables. Okay, I don't call PD, I may call it is differential equation, which is of order n minus 1. So in the case of second order PD, so we can make it a n minus 1 independent variable. That means ultimately it will be uh, reduced to some ODE, and this ODE we can solve to get the solution of the PD. Okay. This is for the particular case where we are dealing with two independent variables, like the topic, today's topic I write the general second order linear partial differential equation. Number 4 is numerical methods. There are certain numerical methods to solve PD, like finite difference method, is one of the method, and another is finite elements method. Spectral method, this is very useful. Spectral method, etc. There are so many others. In spectral method, eigenvalue, eigenvector are these are found, and then it is solved. So there are certain or different numerical techniques or methods from where we can tackle certain types of PD. Okay, so but we are interested in the first technique, like changing the coordinate system to make it a to reduce it a standard form or canonical forms, and then we'll see how to solve it. Okay. Okay, so what are the new set of independent variable? What we actually do for number 1 process. U is equal to uxy and v is equal to vxy. So these two things, particularly u and v, these two are twice continuously, we have to assume that differentiable, and the Jacobian of the transformation, that means del u comma v by del xy, it should not be 0. So what is Jacobian? Prajata, can you tell? This is determinant of ux, uy,
Uy,
vx.
Vx and Vy.
Very good. So its determinant is non-zero. We are expecting that determinant of this thing. This is known as the Jacobian of the transformation. Okay, so this type of transformation we use in case of your change of variables in multiple integrals. Can you recall?
Yes, sir.
Multiple integrals. Yeah. So there also we are assuming that Jacobian has to be non-zero. And because Jacobian is non-zero, its meaning is that the transformation has to be 1-1 transformation. Means injection or injective. Okay, so if the transformation is injective, then we can expect that whatever the initial partial differential equation was there, and whatever the transformed after using the transformation, that partial differential equation, its solution systems are exactly same. Otherwise, you cannot say that the solutions are same. Basically, we need to keep the solution intact, and we want to change it for our beneficiary, means, and then we replace the variables, is not it? So this is our motto, because if we just convert certain differential equation, any differential equation, maybe ODE or PD, to another one which does not preserve the solution, then what's the advantage we are getting? So we have to be sure that it will not change. Okay, that means we have to take the Jacobian is non-zero Jacobian. So the non-vanishing of the Jacobian of the transformation ensure that a 1-1 transformation exists between new and old variables. Okay, this simply means the new independent variables can serve as a new coordinate variable without any ambiguity. Okay, as I just start with certain examples initially. What kind of differential equation or what types of differential equation we are getting? Say, for example, the first one, xyr minus x square minus y square s minus xyt plus py minus qx is equal to twice into x square minus y square. Okay, so first we like to find characteristic equation and characteristic curves. Okay, from there, okay, so this is your one exercise. First, let me tell what is your A, B, and C. What is your A? AR means XY.
xy.
What is your B?
Y square minus x square.
Yes, y square minus x square. What is your C? Minus
Minus
XY.
x.
Okay, so if we look at B square minus 4AC, this is your discriminant. So what it happens? We see that, okay, this is going to be equal to B square means y square minus x square, x square minus 4 into xy. It will be plus, it will be x square y square. Okay, so it will be what it will be? X
Y
square
square plus
plus y
x
square.
square.
Sir,
Whole
x square
whole
plus
square.
y square to the whole square.
Okay, so can I say that it is greater than 0 for all xy belongs to your R2 minus 0, 0. Can I say? Yes. Okay. That means at the origin only it is 0, but except the origin it is positive. That means the whole plane except for this point particularly, if we pick it off the origin, then it is of hyperbolic. Clear? Okay. So, and how to make it hyperbolic, that thing we have to learn. So far we just learn once a given second order differential equation is there, whether what should be your domain of definition, where the function or the partial differential equation is which kind of partial differential equation, it is of hyperbolic or parabolic or elliptic, that you can find. Clear? So hyperbolic, and particularly at the point origin, it is a parabolic at the origin. Can you say it gives elliptic at certain points in the domain? No, because it can never be negative. It's not it.
Yes, sir.
Okay. Okay. Next, we have to learn certain things. What is meant by characteristic equation? Then we will learn the steps. Okay. For this, we have to first learn what is meant by the characteristic equation. Characteristic equation and characteristic curves. Okay. So what is the characteristic equation? This is basically a dy dx square plus b dy dx plus c is equal to 0. Basically, this is minus. Sorry, this would be minus. This is your characteristic equation. And this is a differential equation, you know, first order differential equation. First order ordinary differential equation. And we have to find the solution curves. Say, for example, let lambda 1 x, y and lambda 2 x, y be two real solutions. Then dy by dx minus lambda 1 equal to 0 and dy by dx minus lambda 2 is 0. So I can write this. These are known as the characteristics equation. The solution, this is basically 3 and 4. I can write the solution of 3 and 4. These are known as characteristic curves. Okay. Or simply characteristics. Okay. Okay, let's say we have to find, I like to give one example here. We have to find characteristics, then x square plus twice x y r, sorry, this is s plus y square t is going to be equal to 0. So x square r plus twice x y s plus y square t equal to 0, we have to find the characteristics. Find characteristics. Okay, so for this, first we have to find what is your characteristic equation. This is dy by dx square minus twice xy dy by dx plus y square equal to 0. That means what? Whatever we can say, x dy by dx minus y, its square is going to be equal to 0. That means what? That means dy by dx is equal to y by x, and particularly y by x is equal to c1. That means dy by y is equal to dx by x if we integrate both sides to get the solution, and the solution is y by x is equal to c1. So this is basically your characteristics. Okay, now you see that we are getting only one, because in this case, whatever it is coming, that is a parabolic type. So we'll be getting here 1, 2 times. Then we have to find another thing in such a way that it has to be independent. Okay, so I'll be coming later on. Next, just recall certain things, though you know these things already done by me previous classes. Change of rule. Change rule for one independent variable. Okay, suppose x is equal to gt and y is equal to ht. These are differentiable functions of t, and z is equal to f of xy. Then how we can use the change rule for differentiation, that is dz dt. You want to say? Want to say something? Okay. dz dt is equal to del z del x, because it is a functions of x and y, and dx dt. This you think because x is a function of single variable, that is why it is d, and z is a function of x and y, that is why it is del, plus del z del y, because z is a function of x and y, we have to take both the variables, and dy dt. Okay, this is for the chain rule for one independent variable. Clear? Next, change rule for two independent variables. Chain rule for two independent variables. Okay. Suppose x is equal to g u and v, and y is equal to h u and v are two differentiable functions of u and v, and z is equal to f of x comma y. See, z is a functions of x and y, and x and y are functions of u and v, another two independent variables, but here x and y are single independent variable t, functions of. But here x and y are functions of two independent variables, u and v respectively. Clear? So then whatever we can write chain rule, that is del z del u is equal to del z del x del u. Here it is del x del u. Earlier it was dx dt. You understand, because x is a function of two independent variables, u and v. That is why it is again a partial differentiation. Okay, plus del z del y. It will be del y del u. Here we have to do del z del v. See, z is a function of x and y, two step. Z is a functions of x, y, and x, y are functions of u and v. These two things. Okay, this is happening. So that is why del z del u and then del z del v. So this is del z del x. This is del x del v plus del z del y. This will be del y del v. Clear? So these two rules we have to use several times here once we use the coordinate transformations. Clear? Okay. May I continue another 10 minutes
Sir, we have class now.
at this moment?
Yes, sir, physics.
But there should be one break now.
Sir, only 5 minutes, sir. Like,
It is 5 minutes.
5 minutes, sir.
Okay, so for 5 minutes it is not, then I am not going to start today. Okay, so what I like to tell here, chain rule of differentiation, you have to recall, because this will be necessary for many times in our coordinate transformation or canonical forms. Okay, then I try to tell how we have to set u and v, these two independent new set of independent variables, and what should be the methodology and how to use your means initially whatever your r, s, t, p, q, these things are there. We have to, these things means what? This is zxx, zxy, zyy, zx, zy. Clear? We have to find z uu, zvv, zuv, zu, zv. So these things we have to find. So how we can find? We have to find by using chain rule. Okay, so this much for today.
Thank you, sir.
Okay, welcome.
Thanks.
Let me take the attendance. Okay, so one announcement I like to make.